Okay. I had gotten down to where the first thing I hadn't done was problem number 2. So just to summarize again, a capacitor is a device which stores electric charge. The typical picture is a set of parallel metal plates. There are other geometries. In fact, parallel plates are probably not even the most common way of making a capacitor, but it's the situation where it's easiest to deal with. You have a nice uniform electric field in between there. Anyhow, you have equal and opposite charges on this set of plates. And the higher the voltage, the more charge will get pushed into the capacitor. The charge stored per volt, C equals Q over V. Charge stored per volt is called the capacitance of the device, which depends on how it's made. Factors like how large the plates are and how far apart they are. The exact details of the formula depend on what kind of capacitor it is. You know, you could make a capacitor out of 2 parallel wires instead of 2 parallel plates. It would be wouldn't really have a lot of capacitance, but it would be a different formula, but C is still charge stored per volt. So anyhow, in example number 2, it just kind of changes the numbers some on this picture that's near the top of the page. Instead of 1 centimeter on a side, the plates are a lot bigger. This is definitely not going to fit inside of a cell phone, but find their capacitance. Part A. Well, if you look in your notes from Monday or look at the formula sheet, I should turn that light out. Makes the picture a little better. For parallel plates in a vacuum, the capacitance is given by this. For other geometries, you'd have some other formula, but it always depends somehow on how the thing was constructed. For any given capacitor, C is a constant, unless you start changing the distance between the plates or something. Well, the area and the distance between them they're both given in the question. So the permittivity, epsilon, is 8.85 times 10 to the negative 12th power. It says in the question that the area of each plate is a square meter, and the distance between them is a millimeter. Of course, that has to be converted to meters. So not a lot of hard math there, just moving decimals around, really. 10 to the negative 12 divided by 10 to the negative 3 would be 10 to the negative 9. Capacitance is measured in farads. The charge on each plate, if you were to connect this set of plates to a 12-volt battery, one plate to one terminal of the battery, one plate to the other. The defining equation for capacitance is C equals Q over V, or technically delta V, I guess. Q is the thing we're looking for, find the charge. So multiply both sides by delta V. Fill in the numbers. .06 times 10 to the negative 7 coulombs. A little over a tenth of a microcoulomb. Capacitor combinations. Well, once upon a time, people used to actually repair electrical devices instead of just throw them away and buy another one. And actually, that still occasionally happens if it's some $100,000 piece of medical equipment or something like that. But anyhow, if you want to imagine that it's 1951 and you're repairing somebody's radio for them, you determine that it's this 10 microfarad capacitor right here that's gone bad. And you pull out the little drawer that's labeled 10 microfarads, and wouldn't you know, you're out of them. And you don't really feel like hopping in the car and driving into town to buy one lousy little, probably back then they were 5-cent capacitors. And besides, the store closed 10 minutes ago, you know. So, and an old trick is, you know, next drawer over, got lots of 5s. If you take 2 5s and put them together the right way, they're equivalent to a 10. So you can just solder that in there and it'll work perfectly and you're all set. Now, when we get a little further into this, like that next example there, we have kind of elaborate combinations of capacitors that nobody probably ever put in anybody's radio actually, but well, you know, as with some of this other stuff, it's an exercise. They seem to like to put these kinds of things on standardized exams for one thing. I think I had somebody tell me once there was a question kind of like this on, I think it was probably they call it the MedCat, I think, if you want to go to medical school. Why you have to know this in order to, you know, take out somebody's appendix. I'm not completely sure, but I think it's mostly just that they want smart people cutting into other people with knives. And they kind of use these sorts of things as a filter, you know. But anyhow, to begin at the beginning, there are a couple of different ways that you can well, not only capacitors, but resistors or anything else. There are a couple of different ways that they could be hooked together. Maybe I'll get back to capacitors in just a moment and instead talk about Christmas tree lights. A series circuit is the typical type of Christmas tree lights, you know, the annoying ones, where when one of the bulbs burns out, you could spend the whole afternoon trying to figure out which, I mean, the whole lousy string of lights was only like $11. And if you figure your time is worth anything at all, you might as well just throw them away and buy another light, because yeah, you can buy replacement bulbs, but when they're in series, when one burns out, it breaks the circuit. And so they all turn off. And so you have no way of knowing which one it is. So if you have a bunch of Christmas tree lights in series, an electron comes out of your voltage source and it goes through the first light bulb and it goes through the second light bulb and it goes through the third light bulb. All the electrons go through all the light bulbs in a series circuit. Parallel, well, on a given circuit in your house, all of the various devices are in parallel with each other. the outlets in the wall, the fixture in the ceiling, you know, if you've got a lamp plugged in over here and a radio plugged in over there, and if they're all on the same circuit, you know, leading to the same breaker down in the breaker box in the basement. Well, if a bunch of electrons come out of your voltage source, they get to here and they have a choice of several parallel paths to get back to the other side of this battery I drew here. Some of the electrons would go through the radio, some of the electrons would go through the lamp, some of the electrons would go through the space heater, and whatever else you might be running on that circuit. Okay, so that's the difference between series and parallel. So if, first of all, you have a bunch of capacitors, well, a bunch of anything, doesn't have to be capacitors. I guess I better make some space to write. Looks like I did parallel first. Delta V is the same across each. If you look at the picture on the right, where I drew the parallel circuit, if you follow, you know, the potential is constant along the wire, at least when there's no current flowing through it. Even when there is, usually the resistance of the wires is small, so you only lose 1 or 2 tenths of a volt. But if it's capacitors, there wouldn't be any current at all flowing, and so they would be exactly a constant voltage. So the right-hand side of the battery is connected directly to the right-hand plate in every one of those capacitors. So all of them are at the same potential as the one side of the battery. And the left-hand side of the battery is connected directly to the plate on the left on each of those capacitors. And so each capacitor, you know, if it's a 9-volt battery, each of those capacitors has 9 volts across it. The total charge stored in the entire group if you imagine the capacitors starting out uncharged, and then you connect them to the battery. Well, a whole bunch of electrons, probably have the microphone here. A whole bunch of electrons flows out of the negative side of the battery. They get to here. Some of the electrons decide to go this way and end up on that capacitor. Some of the electrons go this way and end up on that capacitor, and so on and so on. And of course, at the same time that happens, an equal number of electrons is leaving the other side of the capacitors and getting sucked into the positive side of the battery. So the total charge that flowed out of the battery to charge up this group is equal to the charge on number 1 plus the charge on number 2 plus the charge on number 3, and so on. Somebody watching this is going to get seasick. Okay, let's take that equation that I just wrote down and divide it through by the voltage that I just said was the same everywhere. So Q total over delta V equals Q1 over delta V plus Q2 over delta V plus however many more terms there are. I'm trying to be general here. There might be 2 capacitors or there might be 75. Charge stored per volt, that's the definition. That's capacitance, C. So from the fact that C equals Q over delta V, that tells us that EQ for equivalent. In other words, this group of capacitors will have the same effect if you put it into a circuit as one single capacitor would have if that single capacitor had this many microfarads. Okay, this group is equivalent to a single capacitor of CQ. So if you need a 10 and what you've got is a drawer full of 5s, it looks like you want to hook them up in parallel. That'll give you 10 microfarads. Put them in series, you're going to have 2.5 rather than 10. I'll explain that part next. In series, it's the charge that's the same on every capacitor rather than the voltage. Series, same Q on each, because again, imagine that the group starts out uncharged, and then you hook it to the battery. When you hook it to the battery, a whole bunch of electrons comes out of this side of the battery and flows until it gets to the negative plate of the first capacitor. Well, every time an electron comes into one plate of the capacitor, an electron leaves the other side. Hooking this circuit to the battery establishes an electric field inside the wires. And just as that electric field is pushing electrons into the one plate, that same electric field, as it continues around through here, pulls an equal number of electrons out of the other plate of the capacitor. Where do they go? They end up on the left-hand side of the next capacitor. And an equal number of electrons leaves the positive plate of that one and ends up on the negative plate of the next one in line, and so on and so on. So in series, Q1 equals Q2 equal. Instead of plus signs, it's equals all the way across. Same charge on each. As for the voltages, total voltage, called it VT on the picture there. That looks like the spot. This follows from something called the loop rule that I'll get to in probably about a week. But basically what it's saying is, if you've got Christmas tree lights and you plug them into 120 volts, if there's 60 lights in the string, you're going to have 2 volts across each one of those bulbs. So of course, houses are AC, but if you pretend it's direct current, at one end of the string, the first bulb is going to go from 120 down to 118 on the other side of it. With the second bulb, it goes from 118 on one side of it to 116 on the other. and so on. You lose 2 volts across every bulb until you finally get down to 0 on the negative end of the string of lights, or in this case, it's capacitors. So how many volts across the first one plus how many volts across the second one, and so on. That adds up to the total velocity group. Divide that through by the charge that each of them has on it. And then once again, the definition of capacitance. If Q over V is the capacitance, then V over Q would be the reciprocal of the capacitance. So if you had 2 5 microfarad capacitors and you put them in series, 1 over 5 plus 1 over 5 would be 2 over 5. You flip that upside down 5 halves. The pair of 5s would be equivalent to 2.5 if you put them in series. If you want 10, you have to put them in parallel. Well, for something a little more elaborate, we have example number 3. I think I managed to get something even more elaborate than that in the homework. This is unlike, just talking about a pair of 5 microfarad capacitors. This is not just a plug and chug, drop the numbers in and you've got the answer in one step kind of thing, because that's not exactly a series circuit. It's not exactly a parallel circuit. It's what I guess most people would call a series parallel combination. You have to kind of work your way through it in a couple of steps. So the way to begin is to notice that if you just ignore that 10 microfarads that's on top, the rest of it is a couple of capacitors in series. Okay, the 20 and the 40 are in series with each other. So part of the picture looks like that, and that is 2 capacitors in series. So you can throw those numbers into this relationship that's for series. 1 over, I guess I'll call it CS. S for series, the series part of the circuit. Textbook problems are frequently rigged up so that there's a very convenient choice for a common denominator. In the real world, maybe you've got a capacitor that's 47 microfarads and another one that's 110 microfarads, and yeah, not quite such an obvious convenient choice for a common denominator. Something like that, you might want to punch through in decimal form using a calculator. But if you take that approach let me just caution you against round-off errors. If you have something like 1/30, which is 0.03333333, I've seen people round that off to 0.03, and that just changed it by 10%. So if you go, the nice thing about fractions is fractions are exact. If you go using decimals, well, sometimes that's a good idea, but beware of round-off errors. Be sure to carry enough decimal places that it doesn't seriously affect the answer. The other mistake people make is they get this far and then they forget to flip it upside down. This is not the capacitance of these two capacitors. This is 1/C. If 1/C is equal to 3/40, then 40/3 is equal to the equivalent capacitance of those two, roughly 13.3 microfarads. So the three capacitors that you really have are in every way equivalent to as if you had these two. I put what the 20 and 40 are equivalent to in the spot where the 20 and 40 actually are. And that is in parallel with the 10. In parallel, it's just straight addition. So the equivalent capacitance of the entire group is 10 plus 13.3, and the answer is 23.3 microfarads. Before very long, we'll get to equivalent resistance, which are, that's almost the exact same thing. The only difference with resistors is it's switched. With resistors, this is the equation for parallel, and this is the equation for series. Well, actually that's a good place to leave off at exactly 1/4 after. I'm in top form today, I guess.